Hey everybody. Today I wanted to talk about factoring a little bit more and specifically ask the question, is everything factorable? Spoiler, the answer is no, and kind of yes. But anyway, let's get going. So first of all, what do I even mean about factoring? Uh, we've been working with polynomials, quadratics specifically, and trying to convert them from this form called standard form into this form called factored form. A quick reminder, standard form is made up of three different terms, whereas factored form is written as two different parentheses, two different factors. And both forms are equivalent. If we were to graph them, which we will eventually, you'll see that they give us the same picture, but they do serve very different purposes. Here's a bit of a list of the different things, the benefits that each form can provide. In standard form, that's the form that you'd need if you're going to add or subtract it. It's also the format you might need if you wanted to compare it to other polynomials. It's also really easy to see what the degree is when it's written in standard form, because that's just this first number here, and the degree tells us things like how many solutions an equation might have that's got a polynomial in it. Eventually, when we start looking at graphs of these, the standard form will also tell us where the vertex is, and it's really easy to see where the y-intercept is if you have it written in standard form. If you have it written in factored form, it's really easy to multiply or divide because basically you don't even do anything. Here, I just multiplied it by 4, x minus 4. Not a problem. It's also easy to solve equations when something's written in factored form. That's probably the biggest reason we put something in factored form. And eventually when we look at graphs, it will also reveal a different feature that the graph has called its roots. So there's a few benefits, but the question still remains, can everything that's written in standard form be put in factored form? The answer is no. Not every polynomial of this form can be factored. And there's a theorem that says that polynomials written like this, something x squared plus something, can only be factored if those numbers, a, b, and c, in this little expression here, form what we call a perfect square. So perfect square is a number like 1 or 4, or 9, or 16, 25, all the square numbers, right? 8 times 8 is 64, 12 times 12 is 144, and so on. So if you plug numbers into this expression, by the way, this expression is called the discriminant. If you plug numbers into that and it comes out to be a perfect square, then that means it's factorable. And if it doesn't, then you'll not be able to factor it. So let's look at a few examples and see what we mean. Here, x squared plus 6x minus 15. The question is to factor it. So we could pull out a factoring table and try to factor it. But before we go through that effort, let's see if we can see if it even is factorable. And so to do that, I'm going to pull out the discriminant here. And we're going to put in the numbers into it. So instead of b, what we're going to do is put the middle number, which is a 6. And instead of a, I'm going to put the invisible 1 that's in front of the x squared. And instead of c, I'm going to put the negative 15 that's in here. And I'm going to calculate what that gives us. So 6 squared is 36. Over here, 4 times 1 times 15 is 60. And there's 2 negative signs. I'm subtracting a negative 15, and so this is a plus 60. So the discriminant in this case, 36 plus 60, is 96. And 96 is not one of the perfect square numbers. It's between 81 and 100. If you took its square root, you don't get a nice number. You get like a 9-point something sort of number. And what that means is that if we tried to factor x squared plus 6x minus 15, it's not going to work. Now, what does it mean that it's not going to work? I mean, why can't we just put a negative 15 in here and x squared here and come up with a combination of numbers that multiplies up to negative 15 and adds up to 6? Well, let's see. There's 1 and negative 15. There's 3 and negative 5. there's 5 and negative 3 and 15 and negative 1. Those are the only combinations that multiply up to negative 15. And, well, that's the problem. None of them add up to 6. And because I can't come up with a combination of numbers that multiplies to negative 15 and adds up to 6, that means this can't be factored. Now, bunny trail. This actually can be factored. Mathematicians have figured out a way to do it, but they had to invent an entire system of numbers called complex numbers or imaginary numbers. I kid you not, they really do exist. And so if you use those, then you can factor it, and you can factor everything. But we're not going to get into that yet. Come back for Algebra 2 next year, and we'll get into that a little bit more. But anyways, this one, as far as we can tell, isn't really factorable without using those invented imaginary numbers. All right, so why don't we try this one up here a second. Let me pull out the discriminant again and see if we can factor this. So b squared minus 4ac. The b value is this middle number, so that's an 8. And a is the 21 that's in front. And c is the negative 4 that's in the back there. And so I need to calculate what 8 squared minus 4 times 21 times negative 4 is. So let's definitely get out a calculator here. 8 times 8, I know that one. That's 64. But 4 times 21 times 4 is bigger than I can handle. 336. And once again, a minus negative means I'm adding here. So if I add those together, I get 400. So 400 is this perfect square. That is 20 times 20. And so that means that this one can be factored. Real quick, if we wanted to factor that one, I would put a negative 4 into this box and a 21x squared in this box. And 21 and negative 4 multiply up to negative 84. And so I need to now think about a combination of numbers that multiplies to negative 84 and adds up to 8. All right, let's see if we can find a combination of numbers then that multiplies up to negative 84 and adds up to 8. So we've got 1 and negative 84. That adds up to negative 83, certainly not right. We've got 2 and negative 42, 3 and negative 21, I think. No, 28. We've got 4 and negative 21. It doesn't divide by 5 nicely, so I can skip that. We've got 6 and negative 14, and that's close. That adds up to negative 8. I need the opposite pairs, so we want a positive 14 and a negative 6. That's the combination of numbers I need. So we'll put a 14x here and a negative 6x here. And now my goal is what's on the outside. So 21x squared and 14x, they have each divisible by 7 and an x. And that would force this to be a 3 and an x. And 2 times 7 would be 14. And this is a negative 2. Because negative 2 times 3 is negative 6x, and negative 2 times 2 is negative 4. And so final answer here, the factoring is 7x minus 2 and 3x plus 2. All right, so now it's your turn. I want you, in a second, to pause the video and look at these 4 polynomials and figure out which one of them cannot be factored. Most of them can, but there's one that can't. And you do that again by using the b squared minus 4ac test. Why don't you hit pause a moment and try that on your own. So these are the numbers that I got as I calculated them. 432 for the first polynomial, 225 for the one underneath that, 36 and 1. And the only one of these numbers that's not a perfect square is this guy right here, 432. So this one can't be factored, but all the other 3 can. So now that we know that this one can't be factored, but all the other three can, I want you again to hit pause and see if you can factor the remaining three. And when you're done, you can see how I did. So here are most of the work for most of these problems. I got a final answer of x minus 40 and x minus 25 for this problem down here. That was a bit of a struggle because I had to come up with numbers that multiply up to 1,000 and add up to 65, but it wasn't that hard to find a combination. For this problem up here, I needed a combination of numbers that multiplies to -5 and adds up to -4, and that came pretty easily. Final answer is x minus 5 times x plus 1. But then this guy here was a little bit of a challenge. The final answer is down there if you just want to know what that is. But I needed to come up with a combination of numbers that multiplies to 90 and adds up to -19. And so if you start listing those pairs, 1 and 90, 2 and 45, 3 and 30, you realize quickly that you're going to need negative numbers to add up to -19. So -1 and -90, -2 and -45, -3 and 30, -5 and something. I think it's -10 and -9 that you ultimately need here. And so I'll put those in there. And then when you look at the top row, they have an x in common. They're also each triples. And so you'll want to pull out as a greatest common factor a 3x. And 3x times 2x is required to give us the 6x squared. This would have to be a -3 when multiplied by 3 gives us -9. And then this is a -5 because -5 times 2 gives me the -10 I need. And -5 times -3 gives me the +15 I need. And so that's where our final answer comes from. Anyhow, I hope this little test of b squared minus 4ac is a useful one for you. If you find yourself in need of factoring something and you're not sure, can it actually be done or not, or you don't want to go through the effort of trying only to find out that it can't even be done, try calculating b squared minus 4ac. If you don't think you'll ever use this test again, I understand, but I promise you will see b squared minus 4ac in a future video, and you'll use that as part of the quadratic formula to solve problems if you don't like factoring. So anyway, I'll catch you in the next video. Have a great day.